video, we're going to talk about solution stoichiometry. Solution stoichiometry is going to be similar to the stoichiometry we were doing before, where we're using the coefficients in our balanced equation to go between moles of one substance and moles of another substance, except the difference is that instead of starting out with mass and using molar mass to go from grams to moles, we're generally going to start out with volume, and then we're going to use molarity to go between grams and moles. Remember, molarity is moles per liter, so we can use it to convert between moles and liters. Right, molar mass is grams per mole, so we use it to convert between grams and moles. So just the stoichiometry we'd done in the past, right? We had grams of A, right? And then we converted it to moles of A. And we did that using the molar mass of A, right? Once we had moles, then we could convert it to moles of B, right? Remember, we're converting between substances when we're doing stoichiometry. And to do that, we used our coefficients in our balanced equation, right? Our coefficients were our mole-to-mole ratios, if you like that term better. Once I had moles, then we went back to grams. And to do that, we used the molar mass. Molar mass of B, right? So grams to moles using molar mass, moles of one thing to moles of something different using our coefficients, right? Our mole-to-mole ratio. Mole-to-mole ratio. And then for moles back to grams using the molar mass. What we're doing with solution stoichiometry, I spelled stoichiometry wrong here. Usually I'm pretty good with that word. Like, I can't spell lacrosse, but I can usually spell stoichiometry. Right, what we're doing here is we're going to start out with volume of A. And then we're going to convert it to moles. Remember, anytime you're going from one substance to another, it needs to be in terms of moles. And to do that, we're using our molarity of A, right? Remember, molarity, capital M, molarity is moles per liter, so we can use it to convert between those two things, right? Anytime you have something over something, it can be used to convert between those two somethings, right? Grams per mole, we use to convert between grams and moles. If I had the density, grams per milliliter, I use it to convert between grams and milliliters. Molarity is moles per liter, so we can use it to convert between moles and liters. So volume in liters to moles, we can use the molarity. Once I get moles of my first substance, we can convert it to moles of my second, so moles of B. And then we still use our coefficients for that, right? The coefficients in my balanced chemical equation, right? Our mole-to-mole ratio. And then once I have moles, we can go back to volume using the molarity. Sometimes we're actually going from moles to molarity using the volume. So that last step, it just depends what we're solving for. But both the molarity and the volume are involved in that last step. So volume to moles using my concentration, right, in molarity. Moles to moles using my coefficients. So I'm just going to jump in with an example. I think that's the easiest way to learn these. So let's do how many milliliters of sodium hydroxide do we need that's combining the word need and we in the same sentence, in the same word. Do we need to react with a 0.12 to react with 50.00 milliliters of a 0.250 molar Let's do phosphoric acid solution. If the concentration of sodium hydroxide is 0.300 molar. Question mark. So be careful. In the last video, remember with diluting solutions, I said you can only use that, right, that M1V1 equals M2V2 if you're going from one substance to the same substance. Here I'm going from between phosphoric acid and sodium hydroxide, right? How many milliliters of sodium hydroxide are needed to react with that much phosphoric acid? So do not use M1V1 equals M2V2. That does not work for stoichiometry. I know I'm saying this a lot, but really it's so common. Usually about a quarter of my class will do this. Not just my class, but everyone's class. It's a lab issue too. So if you're going from one substance to a different substance, do not use your dilution equation. So I'm not going to use my dilution equation, but I am going to write out some numbers. When there's a lot of numbers in a problem like this, I like to just get it out of the problem. So what I have, whoa, that's not what we wanted. What I have is I have a 0.250 molar phosphoric acid solution, and I have 50 milliliters of it. And then I want to know what is my volume needed to react with a 0.3 molar sodium hydroxide solution. So because I'm going from one substance to another, I need to write my balanced equation. The other thing I'm going to do, and we did this a couple of videos ago where I gave you the unit of concentration as part of the problem, and then I was solving for something different. I do this every time, and I really mean it. Anytime I'm given the unit of concentration as part of the problem, I write it out. I'm not going to keep it as a capital M, because it's really easy to divide when you're supposed to multiply, or multiply when you're supposed to divide if you don't actually have it written out. It's also really easy to miss unit conversions if you don't write it out. So I'm going to rewrite this as 0.250 moles of phosphoric acid for every 1 liter, right? Remember, capital M is moles per liter, so for every 1 liter. And you don't actually have to put the 1 there if you didn't want to, right? We could just say per liter. Which tells me, well, if I'm going to use this volume, that also is going to have to be in liters, so it's not going to, otherwise it's not going to work. So I'm going to convert that to liters, and we can do that in a minute here. The same thing with my sodium hydroxide solution. I'm going to write it out. 0.300 moles of sodium hydroxide for every 1 liter. Put the 1 there, don't put the 1 there, that doesn't matter. What matters is that I'm going to write it out. That way when I do my dimensional analysis, I actually have the units, so I know whether I need to have them on the top or the bottom for them to cancel. So again, anytime, and I really can't think of an exception, anytime I'm given a unit of concentration, so in this case molarity, as part of the problem, I'm going to write it out. I just thought of an exception after I said every time. Diluting solutions, you don't have to because you're plugging it into a formula, right? If you're doing dimensional analysis, you need to write it out. So unless you're plugging it into a formula, write it out. Trust me, it's going to save work in the long run. I do need to convert this to liters, right? Molarity is moles per liter, not moles per milliliter, so I do need my volume in liters. Again, remember there's 10 to the third or 1,000 milliliters in a liter. I'm just going to move my decimal place over 3. So I'm going to get 0.05000 liters. And again, if you don't see that, then do the dimensional analysis, right? 50. Let's do it in a different color. 50 milliliters, and there's 10 to the third milliliters in 1 liter. Those are going to cancel. So 50 divided by 1,000, if you plug that into your calculator, you're going to get 0.05. And then just add those extra zeros for sig figs. The other thing I need is I need my balanced equation, right? I can't convert from one thing to the other without my coefficients. I can't have my coefficients if I don't have my equation, right? If we go back up, right, my coefficients are how we're going to convert. So I need to write my balanced chemical equation. And this is an acid-base reaction. So my phosphoric acid plus my sodium hydroxide. We did these earlier in this chapter. This is where I would kind of break them up, and I would say I have H plus and PO4 3 minus. I have Na with a positive charge and then OH minus. So then the hydrogen and the OH are going to combine, and I'm going to end up with water. Again, I like to think of it as HOH for balancing reasons. And then the sodium with its +1 charge is going to combine with the phosphate, which has a -3 charge. So I'm going to need 3 sodium for every 1 phosphate. And then we do need to balance it. The whole reason we need to write this is we need those coefficients. So I have 3 sodium on my product side. I only have 1 on my reactant side, so I'm going to put a 2 there. That gives me 2 hydroxide. I have, oops, sorry, 3. What am I doing? That's probably what you guys are thinking. What is she doing? 3. I had 3 sodium on my product side, so I need 3 sodium on my reactant side. That also gives me 3 OHs. I have 3 H's in phosphoric acid, so if I put a 3 in front of water, that takes care of that. So my coefficients, you don't have to put the 1 here. I want to talk about it. My coefficients is going to be a 3-to-1 ratio. So problem. Again, I'm just going to do dimensional analysis. So I'm going to start out, if we go back up to kind of our little plan, volume of A, then I'm going to use its molarity to get moles. So I have, and we did this step earlier, 0.05000 liters, right? We converted from milliliters to liters already, and that is of phosphoric acid. If you didn't think to convert it earlier, you would notice this now, because when I go to put in my concentration, right, moles of phosphoric acid per liter, and then you go to cancel them, right, liters and liters, if you would have left milliliters here, then they wouldn't cancel. So you could catch that. In fact, you could do the conversion as part of this problem. You could actually start it with 50 milliliters, divide it by 10 to the 3rd milliliters per liter, and then do this step if you didn't want to do it ahead of time. I am hoping that most of you are comfortable just moving the decimal place over, so you just save yourself that math by just counting three decimal places. So I now have moles of phosphoric acid. Using my balanced chemical equation, there's 1 mole of phosphoric acid for every 3 moles of sodium hydroxide. Because phosphoric acid is on the top, it goes on the bottom. And then my 3 moles of sodium hydroxide go on the top. And moles of phosphoric acid go away. I now have moles of sodium hydroxide. I want volume, so I'm going to use my molarity of sodium hydroxide as the conversion factor. Since moles are on the top, moles have to go on the bottom. So this is the number I'm going to use, and I'm going to put the 3 on the bottom so they cancel. This is where if you didn't write it out, it's not always really straightforward to know whether you have to multiply or divide. So moles per liter, and then those are going to cancel. So I'm going to grab my calculator. 0.05 multiplied by 0.25 multiplied by 3 and then divided by 0.3. So I end up with 0.125 liters of sodium hydroxide. If I go back up to the problem, it actually asked for milliliters. So again, you can use a dimensional analysis step if you want, or you can just move it back over 3 places. So 125 milliliters of sodium hydroxide is my answer. Another example for us. So if 50 milliliters of a 0.200 molar nitric acid solution is combined with 50 milliliters of a 0.150 molar calcium hydroxide solution what is the concentration of calcium nitrates if 23.43 milliliters results? So this problem is a little bit different. The first thing you're going to want to do is just kind of analyze it and figure out what we're doing. So this problem, we're given two reactants, right? We always have two reactants. I should say we're giving information about both of those reactants, right? I'm taking nitric acid and I'm combining it with calcium hydroxide, and I'm given a volume and a concentration of both of those. And then I'm asked to figure out information on a third thing. So even though it doesn't say in this problem, the clue is that I am given information about both reactants. So this is a limiting reactant problem. Again, it doesn't explicitly say that, but if you're given information about two things, both of them reactants, and then you're asked to solve information about a third thing, it is a limiting reactant problem. So remember, whenever we have a limiting reactant problem, what we need to do is we need to first determine which reactant is limiting. So determine which reactant is limiting. And remember, to do that, we're going to convert both of those to moles and then compares the moles that we have to the moles that we need according to our balanced chemical equation, which we'll write here in a minute. So determine which reactant is limiting and then use the limiting reactant to solve the problem. And again, it doesn't say, hey guys, this is a limiting reactant problem, but if you're given information about both reactants and then you're asked to solve for information about something else, you have to figure out which one of those two is limiting. So determine the limiting reactant to solve the problem. So I do need my balanced chemical equation, so we'll write that first. So I have nitric acid, I'm reacting it with calcium hydroxide. Both of those are aqueous. I am producing water plus calcium nitrate, and then I'm just going to balance it for us real quick. It would be good practice for you guys to go and balance it, but I just need a 2 in front of nitric acid and then a 2 in front of water. The rest are aqueous. So I need to figure out, right, solve for moles. Of each reactant. So back up to my information, I have 50 milliliters of a 0.2 molar nitric acid solution. And remember I said, unless we're plugging it into a formula, every time we're giving molarity as part of the problem, I'm going to write it out. So this is 0.200 moles of nitric acid per liter. If I then convert this to liters, and again, I'm just going to move my decimal place over 3, divide by 1,000, however you want to think about it. Don't drop any units on there or any significant figures on there. If I was to multiply my volume in liters by my concentration, liters are going to cancel and I'm going to be left with moles. So if I take 0.05000 liters multiply it by my concentration, which is moles per liter. Those liters are going to cancel. And I get 0.0100 moles of HNO3. So convert your volume to liters, and then when you multiply by your molarity, the liters cancel, and we're left with the number of moles. We're going to do the same thing with calcium hydroxide. So back up to the problem here. I have 50 milliliters again, but this time the concentration is 0.150 molar. So 50 milliliters, 0.150 molar, which again is 0.150 moles, this time of calcium hydroxide per liter. 50 milliliters is 0.05000 liters. So if I multiply those by each other, right, 0.0500 liters multiplied by 0.150 moles per liter, liters cancel, and we get 0.00750 moles of calcium hydroxide. So step 1, solve for moles of each reactant. Our next step, we're going to determine which is limiting and I'm going to do it the way that I did in the previous video where I set up mole ratios. If you wanted to do the whole entire problem, like all the stoichiometry through twice, each time, right, one's using nitric acid and the other time using calcium hydroxide, and then whatever the smaller of your two answers is, that's also fine. You don't have to do it my way. So if you like the other method better, go for it. I'm going to do it this way. So determine which is limiting by comparing the half mole ratio, that's what we just solved for, to the need ratio. The need ratio coming from those coefficients in our balanced equation, right? What I need for this reaction to work perfectly, if I go back up, I need 2 moles of nitric acid for every 1 mole of calcium hydroxide. So I'm going to make a ratio of what I have and compare it to what I need to determine which is limiting. So my have ratio, these are the numbers we just solved for. Remember, I'm going to put the larger of the two numbers on top. So 0.01 is bigger than 0.0075. So what I have, 0.0100 moles of HNO3 for every 0.00750 moles of calcium hydroxide. That is impossible to read. Calcium hydroxide. And then we're going to divide that out. I want to have 1 on the bottom. So 0.01 divided by 0.0075. I get 1.33 nitric acid for every 1 calcium hydroxide. So that's what we have. I'm going back up to my need ratio. My need ratio, again, I'm taking these numbers, they're just my coefficients. So I need 2 nitric acid for every 1 calcium hydroxide. So I need, and you want to put these in the same order as your have ratio. And actually, honestly, I normally do the need ratio first and I put the bigger one on top, and then I do my have ratio in the same order. It works out either way. So I need 2 HNO3 for every 1 CaOH2. If this wasn't already 1 on the bottom, let's say it was 3 to 2, then I would divide it out. I always want to have 1 on the bottom for both of the ratios. So what I need, right? I need 2 nitric acid. I have 1.33 nitric acid. So I don't have as much as I need, right? I don't have enough HNO3 that makes this limiting, right? We need to have less than that, right? We have 1.33, that's less than 2. So when that's your case, the 1 on top is limiting. If I actually had more than I needed, right? Let's say I needed 2, and let's say for some reason it was 2.33, then I have more than I need, so it's excess. Calcium hydroxide would then be limiting. So we determined that HNO3 is limiting, right? I need 2, I have less than that, so that's my limiting reactant. And then I'm going to solve the rest of the problem using my number of moles of HNO3. So back up to our problem. So what we want to know, right, what is the concentration of calcium nitrate if 23.43 milliliters results? And I'm just going to jot that down so I don't have to keep scrolling back up. So 23.43 milliliters of calcium, I might have just said hydroxide, sorry, of calcium nitrate. And we want to know its concentration. What is its molarity? The other piece of information I need is the mole ratio. So we'll just go back up one more time here, hopefully. And I'm converting between nitric acid, because that's my limiting, and calcium nitrate. So this is going to be a 2-to-1 ratio. So when we get to that part in our stoichiometry, for every 2 moles of nitric acid, we're going to produce 1 mole of calcium nitrate. So I'm going to start with nitric acid because that's limiting. I know I said one more time and now I'm scrolling back up because I need that number. I have 0.0100 moles of nitric acid. So that's what we're going to start with. Right? Always start with your limiting. And then our coefficients that we just looked at from my balanced equation said that there was 2 moles of HNO3 for every 1 mole of calcium nitrate. Right? When I do that, my moles of nitric acid are going to cancel. And let's actually just get a number for that. So that's going to equal 0.01, I guess, divided by 2. We really don't need a calculator for that one. 0.0500 moles of calcium nitrate. We're trying to solve for molarity. Remember, molarity is moles divided by liters. So I'm going to take that number, because that's my number of moles. I'm going to divide it by my volume in liters. I have 23.43 milliliters. So again, dividing it by 1,000, moving my decimal place over 3 places. I have 0.02343 liters. So moles divided by my liters is going to get me my molarity. Oop, we lost a 0 in here. There's another 0. Let's just rewrite that. I have it wrong up here too, sorry. If I take 0.01 and divide it by 2, I get 0.00500. Okay. So divide that number by my volume in liters, 0.02343. And I get 0.213 molar. If you want to write it as moles per liter, that's fine. You can just do the capital M for molar.